Niels Bohr's journey toward becoming one of the most influential physicists in history did not begin with sudden flashes of genius or dramatic breakthroughs in a laboratory, but with a childhood immersed in ideas, dialogue, and intellectual openness. He was born in Copenhagen in 1885, at a time when Europe was undergoing profound scientific, cultural, and philosophical transformations. His family home was not merely a place of residence, but a living environment of inquiry, where questions were encouraged and certainty was always open to challenge. Bohr's father, Christian Bohr, was a respected physiologist whose scientific work was grounded in careful experimentation and critical thinking. From him, Niels absorbed the discipline of scientific rigor and the humility required to accept results that might contradict expectations. His mother, Ellen Adler Bohr, came from a family deeply engaged in education, culture, and social responsibility, giving young Niels a broader humanistic perspective that would later shape his philosophical approach to science. In this household, conversation mattered. Ideas were not presented as fixed truths but as proposals to be examined, debated, and refined. This atmosphere left a lasting impression on Bohr. Unlike many scientists who excel primarily through mathematical brilliance or technical skill, Bohr's unique strength lay in his capacity to think deeply about concepts, meanings, and foundations. From a young age, he learned that understanding was not simply about knowing answers, but about asking the right questions. This intellectual habit would later become crucial when he faced problems that resisted conventional thinking. As a student, Bohr showed strong aptitude, but not in a way that immediately marked him as a prodigy destined to revolutionize physics. He was thoughtful, sometimes slow to reach conclusions, and more interested in the implications of ideas than in quick solutions. At the University of Copenhagen, he studied physics at a time when the discipline appeared to be nearing completion. Classical mechanics, electromagnetism, and thermodynamics seemed to explain nearly everything observable in nature. Many leading physicists believed that only minor details remained to be filled in. Yet beneath this apparent completeness, experimental anomalies were quietly accumulating, challenging the foundations of classical theory. Bohr's early academic years coincided with the growing realization that something was deeply wrong with the existing picture of nature. Phenomena related to radiation, atomic spectra, and the interaction between light and matter refused to conform to established laws. These problems fascinated Bohr, not because they promised easy success, but because they pointed toward deeper questions about how nature truly worked. He was particularly drawn to the atom, an entity that had long been treated as a theoretical convenience rather than a concrete physical system with internal structure. During his doctoral studies, Bohr focused on the electron theory of metals, a topic that already hinted at the limitations of classical physics. Although his thesis did not yet contain the revolutionary ideas he would later develop, it revealed his tendency to question assumptions and explore the boundaries of accepted theory. He was not satisfied with surface-level explanations. Instead, he sought coherence between theory and experiment, even when that coherence seemed impossible under existing frameworks. A decisive turning point in Bohr's intellectual development came when he traveled abroad after completing his doctorate. Like many ambitious young scientists of his time, he sought exposure to the leading centers of research. This journey brought him into contact with some of the most influential physicists of the era, including J.J. Thomson in Cambridge and later Ernest Rutherford in Manchester. These encounters were transformative, not only because of the scientific knowledge Bohr gained, but because they exposed him to different scientific cultures and ways of thinking. In Cambridge, Bohr initially struggled to make an impression. Thomson, who had discovered the electron, represented an older generation of physicists deeply rooted in classical intuition. Bohr's ideas did not immediately resonate there, and this experience taught him an important lesson: groundbreaking ideas often face resistance, especially when they challenge deeply held beliefs. Rather than discouraging him, This difficulty strengthened his resolve to think independently. It was in Manchester, working under Rutherford, that Bohr found an environment more receptive to radical thinking. Rutherford had recently proposed a nuclear model of the atom, based on experiments showing that atoms contained a small, dense, positively charged nucleus. This model itself posed serious theoretical problems, particularly regarding atomic stability. Classical physics predicted that electrons orbiting such a nucleus would rapidly lose energy and collapse into it, making atoms inherently unstable. Yet atoms clearly persisted, forming the stable matter of the everyday world. Bohr immediately recognized the significance of this problem. He saw that Rutherford's model, though experimentally grounded, could not be reconciled with classical theory. Instead of trying to force a classical solution, Bohr began to consider whether the emerging ideas of quantization might hold the key. By this time, Max Planck had introduced the concept of energy quanta, and Albert Einstein had applied it to explain the photoelectric effect. These ideas were still controversial, but Bohr sensed that they pointed toward a deeper truth. What set Bohr apart at this stage was not just his knowledge of these new ideas, but his willingness to take them seriously as fundamental principles rather than mathematical tricks. He began to think about the atom not as a classical object behaving in a familiar way, but as something fundamentally different, governed by new rules. This conceptual shift required intellectual courage because it meant abandoning intuitive pictures that had guided physics for centuries. Bohr's early life experiences had prepared him for this leap. Growing up in an environment where questioning was encouraged, where philosophy and science were seen as interconnected, and where uncertainty was not feared, he developed a mindset uniquely suited to confronting the quantum mystery. He did not expect nature to conform to human intuition. Instead, he believed that human understanding must adapt to nature, even when doing so challenged common sense. Equally important was Bohr's developing sense of the relationship between knowledge and language. He was deeply aware that scientific concepts are expressed through words and symbols that carry assumptions from everyday experience. As he grappled with atomic theory, he began to realize that part of the difficulty lay not only in the mathematics, but in the language used to describe atomic phenomena. This sensitivity to conceptual clarity would later become a hallmark of his work and a source of both insight and controversy. By the time Bohr began formulating his atomic model, he was already shaped by a rich blend of influences, a family culture of open inquiry, rigorous scientific training, exposure to experimental breakthroughs, and a philosophical awareness of the limits of classical thinking. His genius did not emerge in isolation but was cultivated through years of reflection, dialogue, and struggle. The revolutionary ideas that would soon transform physics were rooted in this formative period, where Bohr learned to live comfortably with doubt, to respect experimental facts over theoretical elegance, and to pursue understanding even when it required redefining the very meaning of explanation. In retrospect, Bohr's early life reveals an essential truth about scientific creativity. Breakthroughs do not arise solely from technical skill or raw intelligence, but from a willingness to question the foundations of knowledge itself. Bohr's upbringing and intellectual development taught him that certainty can be an obstacle, that progress often begins with admitting confusion, and that the deepest insights come from embracing complexity rather than simplifying it away. These lessons would guide him as he stepped into the heart of the atomic mystery, ready to reshape humanity's understanding of the invisible world that underlies all matter. As Bohr moved from his formative academic years into the threshold of his groundbreaking work, his intellectual character became increasingly defined by a rare combination of patience, depth, and courage. Unlike many scientists who pursued quick recognition or definitive answers, Bohr was comfortable dwelling in uncertainty. He believed that confusion was not a weakness, but a signal that one was approaching something fundamentally important. This attitude was unusual in a scientific culture that often valued clarity and closure above all else. For Bohr, however, the most significant problems were precisely those that resisted easy explanation, and the atom was the greatest of these problems. The early 20th century was a period of tension in physics. Classical mechanics, which had successfully described the motion of planets and projectiles, failed at the atomic scale. Electromagnetism explained light and electricity with remarkable precision, yet could not account for the discrete spectral lines emitted by atoms. These lines were sharp, precise fingerprints of elements, suggesting an internal order within atoms that classical theory could not justify. Many physicists treated these discrepancies as technical details to be resolved within the existing framework. Bohr sensed that they pointed to something far more profound. His time with Rutherford proved decisive because it forced him to confront the atom not as an abstract concept, but as a physical system grounded in experimental evidence. Rutherford's nuclear atom was powerful in its simplicity, a tiny, massive nucleus surrounded by electrons. Yet its theoretical instability made it untenable under classical laws. Bohr understood that this contradiction was not a flaw to be patched over, but a doorway to a new understanding of nature. Instead of discarding Rutherford's model, he chose to question the assumptions used to analyze it. This decision marked a turning point in Bohr's thinking. He began to entertain the possibility that classical physics was not universally valid, that its laws might break down at very small scales. This was a radical idea because classical physics had been extraordinarily successful for centuries. To suggest its limits was to challenge the intellectual authority of the entire discipline. Yet Bohr's upbringing had taught him that respect for tradition should never override respect for truth. If experiments contradicted theory, then theory must change. Bohr's willingness to integrate quantization into atomic structure was an act of intellectual synthesis. He did not invent the quantum idea, but he recognized where it truly belonged. By proposing that electrons could exist only in certain allowed states, he introduced a new kind of explanation that was neither purely classical nor fully understood even by himself. He openly admitted that his model was incomplete and conceptually strange. What mattered was not that it conformed to intuition, but that it made sense of observations. This honesty about the provisional nature of knowledge became a defining feature of Bohr's scientific personality. He did not present his ideas as final truths, but as steps toward deeper understanding. This approach fostered a culture of open inquiry around him. Younger physicists felt encouraged to explore bold ideas without fear of immediate rejection. Bohr's influence thus extended beyond his own work, shaping the development of an entire generation. Equally important was Bohr's growing realization that the challenges of atomic physics were not only mathematical but conceptual. He saw that traditional notions such as trajectory, position, and causality might not apply in the same way at the quantum level. This realization did not come easily. Bohr struggled intensely with these ideas, often revising his views and engaging in long discussions with colleagues. His thinking evolved slowly, through dialogue rather than sudden insight. This slow, reflective process was sometimes mistaken for indecision. In reality, it was a sign of intellectual responsibility. Bohr understood that revolutionary ideas carried deep implications, not only for physics but for how humans understand reality. He felt a duty to articulate these ideas carefully, aware that careless language could mislead or oversimplify. This concern for clarity, paradoxically, often led him to express himself in ways that others found obscure. Yet behind his dense language lay a profound sensitivity to the limits of expression itself. Bohr's early development also shaped his views on the relationship between theory and experiment. He rejected the idea that theory should dictate what experiments mean. Instead, he believed that experiments define the questions theory must answer. This stance placed him firmly on the side of empirical humility. Nature, not human preference, was the ultimate authority. This principle guided him throughout his career and became central to his interpretation of quantum mechanics. Another crucial aspect of Bohr's intellectual formation was his ethical awareness. He did not see science as an isolated pursuit divorced from society. Even in his early years, he was conscious of the broader implications of scientific knowledge. This awareness would later influence his views on nuclear weapons and international cooperation, but its roots lay in his formative period, where science and human values were discussed side by side. As Bohr's ideas matured, it became clear that his genius lay not in providing definitive answers, but in reframing questions. He shifted the focus of physics from asking how nature must behave to asking how nature can be meaningfully described. This subtle change had enormous consequences. It opened the door to a view of science in which knowledge is contextual, limited, and deeply connected to the conditions under which it is obtained. By the time Bohr fully entered the quantum debate, he was intellectually equipped to handle its paradoxes. His early life had taught him patience, his education had trained his analytical skills, and his experiences abroad had exposed him to the limits of established thinking. These elements combined to produce a scientist uniquely suited to navigate the strange landscape of the quantum world. Looking back, it becomes evident that Bohr's early intellectual journey was not merely a prelude to his later achievements, but an essential foundation for them. The habits of thought he developed, the values he embraced, and the questions he learned to ask all played a decisive role in shaping modern physics. His story reminds us that scientific revolutions are not born solely in equations or experiments, but in minds prepared to question, to listen, and to accept that reality may be far stranger than our most cherished intuitions. In understanding Bohr's early development, we gain insight into the nature of scientific creativity itself. It is not a linear path toward truth, but a complex process of exploration, doubt, and reinterpretation. Bohr's life illustrates that progress often requires letting go of familiar ideas and embracing uncertainty as a guide rather than an obstacle. This mindset, forged long before his most famous contributions, allowed him to unlock the quantum atom and, in doing so, transform humanity's understanding of the physical world. At the dawn of the 20th century, physics stood at a strange crossroads. On the surface, it appeared triumphant, almost complete. The laws of motion formulated centuries earlier described the movement of planets with astonishing accuracy. Electromagnetism unified electricity, magnetism, and light into a single elegant framework. Thermodynamics explained heat, energy, and entropy with mathematical precision. Many leading scientists believed that nature had essentially revealed all its fundamental secrets, and that future generations of physicists would spend their careers refining measurements to ever greater decimal places. Yet beneath this confidence, cracks were forming, and these cracks would soon widen into a crisis that classical physics could not survive. The atom sat at the center of this growing tension. For much of the 19th century, atoms were treated as convenient theoretical constructs rather than physical realities with internal structure. They helped chemists explain reactions and physicists describe gases, but few worried about what atoms actually were. As experimental techniques improved, however, the atom could no longer remain an abstract idea. Evidence began to accumulate that atoms emitted and absorbed light in highly specific ways. When elements were heated or electrified, they produced sharp spectral lines, precise frequencies of light that formed distinct patterns. Each element had its own unique spectral signature, like a fingerprint written in light. Classical physics, which described radiation as a continuous wave phenomenon, could not explain why these emissions were discrete rather than continuous. This problem was not a minor anomaly. It struck at the heart of classical theory. According to classical electromagnetism, an accelerating electric charge should continuously radiate energy. In the atomic picture that began to emerge, electrons were imagined as orbiting the nucleus much like planets orbit the sun. If this were true, electrons should continuously lose energy, spiral inward, and collapse into the nucleus in a fraction of a second. Matter itself should be unstable. The fact that the world around us clearly existed made this prediction absurd, yet classical physics offered no alternative explanation. At first, many physicists hoped these difficulties could be resolved with clever adjustments. Perhaps atoms were not quite like miniature solar systems, or perhaps unknown forces stabilized electron orbits. There was a strong desire to preserve classical ideas because they had proven so successful elsewhere. The notion that entirely new principles might be required was unsettling. Classical physics was deeply intuitive, rooted in everyday experience of motion, forces, and continuity. To abandon it felt like abandoning common sense itself. The crisis deepened as more experimental results emerged. One of the most troubling involved blackbody radiation, the spectrum of light emitted by heated objects. Classical theory predicted that such objects should emit infinite energy at high frequencies, a nonsensical result later known as the ultraviolet catastrophe. Experiments showed a very different behavior. Energy emission dropped sharply at high frequencies. To resolve this, Max Planck introduced a radical assumption in 1900, proposing that energy could only be emitted or absorbed in discrete units, later called quanta. Planck himself initially viewed this as a mathematical trick rather than a statement about physical reality, but it worked remarkably well. Soon after, Albert Einstein took the quantum idea even further. In explaining the photoelectric effect, he proposed that light itself behaved as if it were made of discrete packets of energy. This idea challenged the wave theory of light, which had been firmly established by experiments. Einstein's explanation matched experimental results perfectly, yet it implied that light had a dual nature, behaving sometimes like a wave and sometimes like a particle. Classical physics had no room for such ambiguity. Despite these developments, many physicists remained reluctant to accept that quantization was a fundamental feature of nature. The quantum appeared as an intrusion, a patch applied where classical theory failed. It was within this intellectual climate that the atom emerged as the ultimate test case. If classical physics could not explain the stability and behavior of atoms, then its claim to universality was seriously undermined. The discovery of the atomic nucleus by Ernest Rutherford intensified the crisis. His experiments showed that atoms consisted mostly of empty space, with a tiny, dense nucleus at the center. This model was experimentally compelling, but theoretically disastrous. Classical physics predicted immediate atomic collapse, yet experiments contradicted this prediction at every turn. The contradiction was no longer subtle, it was stark and unavoidable. For many scientists, this situation was deeply troubling. Physics had long been admired for its logical coherence and predictive power. Now, its most trusted principles were producing nonsense at the most fundamental level of matter. The crisis was not merely technical, but philosophical. It forced physicists to confront the possibility that their most basic assumptions about reality were incomplete or even wrong. The atom thus became the battlefield where old ideas fought for survival against emerging evidence. Some researchers attempted increasingly complex classical models, hoping that hidden mechanisms might restore stability. Others began to suspect that the very concepts of trajectory, continuity, and determinism might not apply at atomic scales. This suspicion marked a profound shift in scientific thinking. It suggested that nature might not be fully describable in terms of familiar, intuitive concepts. This growing sense of conceptual unease created an opening for new ideas. The crisis of classical physics was not a sudden collapse, but a gradual erosion of confidence. Each new experiment that defied explanation weakened the old framework a little more. By the time Niels Bohr entered the scene, the intellectual ground was already unstable, though many still clung to the hope that classical physics could be saved. What made this crisis particularly significant was its scope. It was not confined to a single phenomenon or experimental anomaly. It spanned radiation, matter, energy, and the very nature of physical explanation. The atom, once thought to be a simple building block, had become a source of deep mystery. Understanding it required confronting questions about how nature stores and releases energy, how light interacts with matter, and how stability arises from apparent chaos. The crisis also exposed the limits of reductionism as it was traditionally understood. Classical physics assumed that complex systems could always be understood by analyzing their parts in isolation. The atomic crisis suggested that this approach might fail at fundamental levels. The behavior of electrons could not be explained simply by applying known laws to individual particles. Something about the system as a whole mattered, something that could not be captured by classical reasoning alone. As debates intensified, the physics community became divided. Some viewed the emerging quantum ideas as temporary tools, useful but incomplete. Others sensed that they represented the beginning of a new paradigm. What was clear to all, however, was that the atom had become the key to resolving the crisis. Whoever could explain its stability and behavior would determine the future direction of physics. This intellectual tension created a unique historical moment. The old framework was no longer adequate, but the new one was not yet fully formed. Physicists were navigating uncharted territory, guided by experimental results, but lacking a coherent theoretical map. It was into this uncertain landscape that Niels Bohr would step, bringing with him a willingness to question assumptions and to accept explanations that defied classical intuition. The crisis of classical physics was thus not merely a background to Bohr's work, but a driving force behind it. Without this crisis, there would have been no need for radical ideas about atomic structure. The failure of classical theory created both the necessity and the opportunity for innovation. It forced physicists to confront the possibility that nature operates according to principles fundamentally different from those governing everyday experience. In retrospect, this crisis can be seen as a turning point in the history of science. It marked the moment when physics began to accept limits to classical description and opened itself to new forms of explanation. The atom, once an abstract concept, became the gateway to a deeper understanding of reality. The struggle to explain it revealed that the universe at its smallest scales is not smooth and continuous, but discrete, probabilistic, and deeply counterintuitive. This realization did not come easily or quickly. It emerged from decades of experimental frustration and theoretical struggle. Yet it was precisely this struggle that prepared the ground for a new vision of nature. The crisis of classical physics was painful, unsettling, and disruptive, but it was also profoundly creative. It cleared the way for a revolution that would transform science, technology, and philosophy alike, reshaping humanity's understanding of the atom and, ultimately, of the universe itself. As the crisis deepened, physicists began to realize that the problem was not confined to isolated experiments, but reflected a fundamental mismatch between classical concepts and atomic reality. Classical physics relied on continuity, smooth motion, continuous energy exchange, and well-defined trajectories. At the atomic scale, however, experiments repeatedly suggested discontinuity. Energy appeared in fixed amounts, transitions happened abruptly, and outcomes depended on conditions in ways that defied deterministic prediction. This was not merely inconvenient, it was conceptually destabilizing. Physics had long prided itself on explaining nature through clear causal chains, yet the atom seemed to refuse such clarity. The emotional and intellectual impact of this realization should not be underestimated. For many scientists trained in the classical tradition, these anomalies felt like a betrayal of the very principles that had defined their discipline. There was resistance not because the data were unclear, but because the implications were unsettling. Accepting that classical physics might fail at a fundamental level meant accepting that human intuition, shaped by everyday experience, was not a reliable guide to reality. This challenged the implicit belief that the universe must be understandable in terms that feel natural to the human mind. The atom became a symbol of this tension. On one hand, it was experimentally accessible through spectroscopy and scattering experiments. On the other hand, it remained theoretically elusive. Attempts to visualize electrons as tiny balls orbiting a nucleus ran into immediate contradictions. Attempts to abandon visualization altogether left physicists with abstract equations disconnected from physical meaning. The community oscillated between clinging to familiar pictures and venturing into increasingly abstract territory. During this period, debate intensified around the role of models in science. Classical models had always served as intuitive bridges between mathematics and reality. Now, models seemed to mislead as much as they helped. The atomic crisis forced physicists to ask whether a model must resemble reality in a visual sense, or whether it could be purely symbolic and still meaningful. This question would later become central to quantum theory, but its roots lay in the frustration of trying to reconcile atomic behavior with classical imagery. Another source of unease was the growing role of probability. Classical physics was deterministic. Given complete information about a system, its future could be predicted exactly. Atomic phenomena, however, seemed to resist such prediction. Even when experiments were carefully controlled, outcomes varied in ways that could only be described statistically. At first, many physicists assumed this randomness reflected experimental imperfections or hidden variables. The idea that probability might be fundamental, not just a reflection of ignorance, was deeply troubling. This tension revealed a deeper philosophical conflict about the nature of scientific explanation. Was the goal of physics to describe an objective reality independent of observation, or to provide reliable rules for predicting experimental outcomes? Classical physics had comfortably assumed both were possible at the same time. The atomic crisis suggested that this assumption might no longer hold. Experiments showed that the act of measurement itself could not be separated from what was being measured, blurring the boundary between observer and system. As these issues accumulated, the sense of crisis transformed into a sense of transition. Physicists began to recognize that they were not merely solving puzzles within an established framework, but standing at the threshold of a new one. This realization brought both anxiety and excitement. The old rules were failing, but new possibilities were emerging. The atom, once a source of frustration, became a gateway to deeper insights about nature. The generational divide within physics became more pronounced. Older physicists often viewed quantum ideas with suspicion, hoping that a return to classical reasoning would eventually resolve the anomalies. Younger physicists, less invested in tradition, were more willing to explore radical alternatives. Yet even among the young, there was uncertainty. The quantum ideas lacked coherence, and no single theory unified them. They appeared as fragments rather than a complete picture. What made this period especially challenging was the absence of a clear guiding principle. In earlier revolutions, such as the transition from Aristotelian to Newtonian physics, new frameworks quickly demonstrated their superiority. In the quantum case, progress was uneven and conceptually confusing. Success in explaining one phenomenon often created new problems elsewhere. The atom was partially explained, then plunged back into mystery. The instability of classical concepts also affected how physicists communicated with one another. Language itself became problematic. Terms like particle, wave, orbit, and trajectory carried classical meanings that no longer applied cleanly. Yet there were no established alternatives. Physicists struggled to describe what they were discovering without misleading themselves or others. This linguistic struggle was not superficial. It reflected the deeper challenge of thinking about a reality that resisted familiar categories. Despite the confusion, certain lessons gradually became clear. One was that experimental results must be taken seriously, even when they contradict deeply held beliefs. Another was that theoretical elegance could no longer be the sole criterion for truth. A theory might be conceptually disturbing and still be correct. These lessons marked a shift in scientific values, emphasizing empirical adequacy and conceptual humility over intuitive appeal. The crisis also highlighted the creative role of failure in science. Each failed attempt to explain atomic behavior using classical ideas revealed more clearly where those ideas broke down. These failures were not wasted effort, they mapped the boundaries of applicability for classical physics. By showing what could not work, they clarified what needed to change. In this sense, the crisis was productive as well as disruptive. As understanding deepened, it became apparent that the atom was not simply a smaller version of macroscopic systems, but a fundamentally different kind of entity. Its behavior could not be extrapolated from everyday experience. This realization undermined the assumption that the laws governing the large and the small must be identical. Instead, it suggested a layered view of reality, where different levels required different descriptive frameworks. This layered view carried profound implications. It implied that scientific knowledge might always be partial, valid within certain domains but not universally applicable. Classical physics remained extraordinarily successful for macroscopic phenomena, but its authority ended at the atomic scale. This did not diminish its value, it clarified its scope. The recognition of limits became a source of strength rather than weakness. By the time the atomic crisis reached its peak, the physics community had undergone a subtle transformation. Even before a fully coherent quantum theory emerged, many physicists had accepted that classical physics was no longer the final word on nature. The idea that fundamental reality might be probabilistic, discontinuous, and context-dependent was gaining ground, even if it remained deeply uncomfortable. This shift prepared the intellectual environment for a new kind of thinker, someone willing to work without the reassurance of classical intuition and to accept explanation without visualization. The crisis of classical physics was thus not only a breakdown, but a preparation. It cleared space for new concepts, new methods, and new philosophies of science. The atom, which had exposed the failure of classical ideas, would soon become the foundation of a new theoretical framework. The struggle to understand it reshaped physics from the inside, altering not only what scientists believed about nature, but how they believed knowledge itself should be constructed. Out of confusion emerged a readiness for revolution, a willingness to rethink the deepest assumptions of the discipline. In this sense, the crisis was both an ending and a beginning. It marked the end of the belief that classical physics could explain everything, and the beginning of a more nuanced understanding of reality. The atom had forced physics to confront its own limitations, and, in doing so, opened the path toward one of the most profound transformations in the history of human thought. When Niels Bohr began to focus intensely on the problem of atomic structure, he was stepping into the very center of the scientific storm. The atom had already been identified as the weak point of classical physics, and Rutherford's nuclear model had sharpened the problem rather than solved it. Bohr understood that the question was no longer whether the atom had internal structure, but how that structure could exist without collapsing under the known laws of physics. Classical reasoning failed so completely that any genuine solution would require not refinement, but transformation. Bohr's atomic model emerged from this realization, not as a polished theory, but as a daring conceptual leap that redefined what it meant to explain nature. The starting point for Bohr was Rutherford's nuclear atom, which placed a small, positively charged nucleus at the center, with electrons moving around it. Experimentally, this picture made sense. The scattering of alpha particles showed that most of an atom's mass and positive charge were concentrated in a tiny core. The difficulty was theoretical. According to classical electrodynamics, an electron moving in a curved path is accelerating, and an accelerating charge must radiate energy continuously. As it radiates energy, it should slow down and spiral into the nucleus. Calculations showed that this collapse would occur almost instantly. Yet atoms were stable, matter persisted, and chemistry existed. Bohr saw that this contradiction was not a technical flaw, but a fundamental incompatibility between classical laws and atomic reality. Rather than abandoning Rutherford's model, Bohr made a radical choice. He decided to abandon the classical assumption that electrons could have any arbitrary energy. Drawing inspiration from the quantum ideas introduced by Planck and Einstein, Bohr proposed that electrons in atoms could occupy only certain allowed states, each with a specific, fixed energy. While an electron remained in one of these states, it did not radiate energy, no matter how counterintuitive that seemed from a classical perspective. Radiation occurred only when an electron transitioned between these states, emitting or absorbing a quantum of energy equal to the difference between them. This idea shattered the classical picture of continuous motion and energy exchange. In Bohr's model, the atom was governed by rules that permitted stability precisely because they forbade certain behaviors. Electrons were not free to lose energy gradually. They could only jump between discrete energy levels. These jumps were instantaneous and could not be described in terms of classical trajectories. Bohr openly acknowledged that this behavior could not be visualized using familiar concepts. The model worked not because it was intuitive, but because it aligned with experimental facts. One of the most striking successes of Bohr's model was its ability to explain the spectral lines of hydrogen. For decades, spectroscopists had cataloged these lines with great precision, but no theory had explained why they appeared at specific frequencies. Bohr showed that when an electron in a hydrogen atom jumped from a higher energy level to a lower one, it emitted light with a frequency determined by the energy difference between the levels. Using simple mathematical relationships, he derived a formula that matched the observed spectral lines exactly. This was a stunning achievement. It transformed spectroscopy from an empirical catalog into a window into atomic structure. The success of this explanation gave Bohr's model immediate credibility, even among those who found its assumptions disturbing. It demonstrated that quantum ideas were not merely abstract speculations, but essential tools for understanding real physical systems. At the same time, it revealed the limits of classical explanation. Concepts like orbit and trajectory remained in Bohr's model, but they no longer carried their classical meaning. They became symbolic placeholders rather than literal descriptions of motion. Bohr was fully aware of the provisional nature of his model. He did not claim that it represented a complete or final picture of the atom. Instead, he presented it as a framework that captured certain essential features while leaving others unresolved. This honesty was part of its strength. Bohr understood that he was working in a transitional period where old concepts were being stretched beyond their limits and new ones were not yet fully formed. A crucial aspect of Bohr's atomic model was the way it redefined explanation itself. In classical physics, to explain a system meant to describe its motion in detail over time. In Bohr's theory, explanation took a different form. It consisted of identifying allowed states and the rules governing transitions between them. The continuous story of motion was replaced by a discrete set of possibilities. This shift marked a profound change in scientific thinking. It suggested that at a fundamental level, nature might not tell a continuous story at all. The model also introduced a new relationship between theory and experiment. Bohr did not derive his rules from first principles. He inferred them from experimental regularities and imposed them as postulates. This approach was unusual and even uncomfortable for many physicists who were accustomed to deriving laws from deeper theoretical foundations. Bohr accepted this discomfort as a temporary necessity. He believed that understanding had to begin where experiments led, even if the theoretical justification came later. Bohr's atomic model also challenged the idea that physical laws must be universally applicable. Classical laws worked extraordinarily well for macroscopic systems, but Bohr's theory implied that they broke down at atomic scales. This was not a failure of classical physics, but a recognition of its domain of validity. Bohr introduced the notion that different levels of reality might require different descriptive frameworks, each internally consistent but not reducible to the others. The philosophical implications of this view were far-reaching. If atomic behavior could not be fully described in classical terms, then the goal of physics could no longer be to provide a single, unified picture of reality based on everyday intuition. Instead, physics would have to accept a plurality of descriptions, each suited to specific contexts. Bohr did not yet articulate this idea fully, but it was implicit in his model and would later become central to his thinking. Another important feature of Bohr's model was its emphasis on limits. Certain quantities, such as angular momentum, were quantized, meaning they could take only specific values. This quantization imposed constraints on atomic behavior that had no classical analog. It was as if nature itself enforced rules that prevented certain states from existing. Stability arose not from balance of forces alone, but from the exclusion of forbidden possibilities. This idea of stability through restriction was deeply counterintuitive. Classical physics explained stability through equilibrium, where opposing forces balanced each other. Bohr's atom was stable because certain transitions simply could not occur. This represented a shift from dynamic explanations to structural ones. The structure of allowed states determined behavior more fundamentally than forces acting in time. Bohr's willingness to accept such unconventional explanations reflected his broader intellectual character. He was less concerned with preserving familiar pictures than with capturing essential relationships. He recognized that insisting on classical visualization could become an obstacle rather than a guide. By loosening the grip of classical imagery, he opened the door to a more abstract but more accurate understanding of atomic phenomena. Despite its success, Bohr's model also faced significant limitations. It worked best for hydrogen and hydrogen-like atoms, but struggled to explain more complex systems. It could not account fully for the intensities of spectral lines or the detailed behavior of multi-electron atoms. Bohr knew these shortcomings well. He viewed them not as failures, but as signs that deeper principles were still waiting to be discovered. The atomic model thus occupied a unique position in the history of science. It was neither purely classical nor fully quantum in the modern sense. It combined classical elements with quantum postulates in a way that was internally inconsistent by later standards. Yet this hybrid character was precisely what made it effective during a period of transition. It provided a bridge between old and new ways of thinking. For the physics community, Bohr's model was both a solution and a challenge. It solved specific problems with remarkable accuracy, but it also raised new questions about the nature of explanation, reality, and knowledge. It forced physicists to confront the possibility that fundamental processes could not be visualized or described in familiar terms. In doing so, it prepared the ground for the more radical formulations of quantum mechanics that would follow. In this sense, Bohr's atomic model was less a final answer than an invitation. It invited physicists to rethink their assumptions, to accept provisional rules, and to explore a world where stability emerged from quantization rather than continuity. It showed that understanding could advance even when conceptual clarity lagged behind mathematical success. The genius of Bohr lay not only in proposing a model that worked, but in recognizing what that success implied. It implied that nature at its most fundamental level might resist classical description altogether. By daring to propose rules that defied intuition yet matched reality, Bohr changed the direction of physics. His atomic model became the foundation upon which modern quantum theory would be built, not because it was complete, but because it revealed, with unprecedented clarity, the path forward. As the implications of Bohr's atomic model began to sink in, it became clear that its true significance extended far beyond its immediate successes. What Bohr had introduced was not simply a new picture of the atom, but a new attitude toward scientific explanation. His model forced physicists to confront a deeply unsettling idea that at the most fundamental level, nature might not be fully describable in terms of continuous motion and cause and effect relationships unfolding smoothly in time. This realization reshaped the intellectual landscape of physics and set the stage for the quantum revolution that followed. One of the most profound consequences of Bohr's model was the way it redefined the role of classical concepts. Terms like orbit, energy, and angular momentum were retained, but their meanings were transformed. Orbits were no longer paths traced by electrons in space in the classical sense. They were labels for allowed states. Energy was no longer a quantity that could vary continuously, but one that came in discrete steps. These conceptual shifts created a sense of unease. because they blurred the line between physical reality and mathematical description. Physicists were accustomed to believing that their theories described what was really happening. Bohr's model suggested instead that theories might only describe what could be said about nature under specific conditions. This tension sparked intense debate. Some critics argued that Bohr's model was merely a clever calculation tool lacking true explanatory power. They objected to its reliance on postulates rather than derivations, and to its apparent inconsistency with classical laws. Others saw in it a necessary compromise, a temporary framework that captured essential features of atomic behavior while awaiting a deeper theory. Bohr himself accepted this ambiguity. He did not claim that his model revealed the ultimate reality of the atom. He viewed it as a step toward understanding, guided by experimental facts rather than philosophical comfort. The model's success in explaining hydrogen spectra gave it enormous influence, but it also highlighted its limitations. When physicists tried to apply it to more complex atoms, they encountered difficulties. Electron-electron interactions, fine spectral details, and chemical bonding all lay beyond its reach. These failures were not discouraging, they were informative. They showed that the quantum idea was indispensable, but that the specific form of Bohr's model was incomplete. In this way, the model functioned as a diagnostic tool, revealing both what worked and what needed rethinking. Another crucial aspect of Bohr's contribution was his insistence that contradictions between classical and quantum ideas should not be ignored or hidden. Instead of trying to force quantum behavior into classical categories, Bohr argued that these contradictions pointed to the limits of classical description. He believed that physics had reached a point where familiar concepts could no longer be applied without modification. This belief required intellectual humility. It meant accepting that the language and intuitions developed through everyday experience might be inadequate for describing atomic phenomena. This humility shaped the way Bohr approached theoretical development. He was not driven by the desire to construct a perfectly consistent mathematical system at all costs. Rather, he prioritized coherence with experimental evidence and conceptual honesty. If a theory required rules that could not be visualized or intuitively justified, Bohr was willing to accept that, provided those rules made sense of observations. This stance contrasted with that of many contemporaries, who hoped that a return to classical reasoning would eventually restore intuitive clarity. Bohr's model also altered how physicists thought about causality. In classical physics, causality was continuous and local. One state of a system led smoothly to the next. In Bohr's atom, transitions occurred abruptly, without a describable intermediate process. An electron did not gradually move from one orbit to another, it jumped. What happened during this jump could not be described within the theory. This challenged the assumption that every physical process must be describable in detail. It suggested that explanation might sometimes consist of rules governing observable outcomes, rather than stories about underlying mechanisms. This shift had far-reaching philosophical consequences. It raised questions about what it means to understand a phenomenon. Is understanding achieved by visualizing a process, or by being able to predict outcomes reliably? Bohr leaned toward the latter view, though he never dismissed the value of conceptual insight. He simply recognized that at the quantum level, prediction and explanation might take forms unfamiliar from classical science. The atomic model also influenced how physicists thought about measurement. In Bohr's framework, the properties of an atom were defined in relation to specific transitions and observations. Energy levels were inferred from emitted or absorbed radiation, not observed directly. This reliance on measurement outcomes foreshadowed later debates about the role of observation in quantum mechanics. Bohr began to see that the act of measurement was not a passive revelation of pre-existing properties, but an active interaction that played a role in defining what could be known. This realization gradually led Bohr to a more general philosophical position, though it would take years to articulate fully. He began to suspect that atomic phenomena could not be separated from the conditions under which they were observed. Theories, in this view, did not describe an observer, independent reality in the classical sense, but rather provided frameworks for organizing and communicating experimental experiences. This was a radical departure from the traditional goal of physics, and it placed Bohr at the center of some of the most intense philosophical debates of the 20th century. Despite these controversies, the practical impact of Bohr's atomic model was undeniable. It gave physicists a concrete way to think about atoms, guided experiments, and inspired new lines of inquiry. It provided a common reference point around which discussions could revolve. Even those who disagreed with its assumptions had to engage with it, because it explained facts that no other theory could. The model also played a crucial educational role. It introduced generations of students and researchers to the idea that atomic behavior is governed by quantized states. Although later theories would replace Bohr's orbits with more abstract constructs, the core insight of discrete energy levels remained central. In this sense, Bohr's model became a gateway into quantum thinking, a first step into a world where familiar rules no longer applied. Perhaps the most enduring legacy of the atomic model lies in how it changed the criteria for scientific success. Before Bohr, a good theory was expected to be intuitive, continuous, and grounded in classical concepts. After Bohr, success could mean something very different. A theory could be counterintuitive, discontinuous, and conceptually challenging, yet still be considered deeply successful if it captured essential features of reality. This redefinition of success opened the door to more radical theories, including wave mechanics and matrix mechanics, which would soon supersede Bohr's model. Bohr's willingness to accept incompleteness also set a powerful example. He showed that it is possible to make profound progress without having all the answers. By proposing a model that worked in key cases while openly acknowledging its limitations, he encouraged a culture of exploration rather than dogmatism. This culture proved fertile ground for innovation. Younger physicists felt empowered to push beyond the model, knowing that even imperfect frameworks could yield deep insights. As quantum mechanics developed, many elements of Bohr's atomic model were abandoned or reinterpreted. Orbits gave way to probability distributions, and jumps were described in terms of wave functions and operators. Yet the spirit of Bohr's approach endured. His insistence on respecting experimental facts, his acceptance of conceptual limits, and his emphasis on the contextual nature of description became central to the mature quantum theory. In hindsight, the atomic model can be seen as a pivotal moment in the history of science. It marked the point at which physics decisively broke with the classical worldview and embraced a new, more abstract conception of nature. The model's hybrid character, blending classical imagery with quantum rules, reflected the transitional state of understanding at the time. It was a bridge between worlds, enabling physicists to cross from the familiar terrain of classical physics into the strange landscape of the quantum. The genius of Bohr's contribution lies not in the permanence of his specific model, but in the transformation it initiated. By daring to propose rules that contradicted classical expectations yet matched experimental reality, Bohr demonstrated a new way of doing physics. He showed that fidelity to nature must come before fidelity to intuition, and that explanation must sometimes be redefined to accommodate what nature reveals. Through his atomic model, Bohr unlocked more than the structure of the atom. He unlocked a new way of thinking about science itself, one that accepts uncertainty, embraces abstraction, and recognizes the limits of human intuition. This shift would shape the development of modern physics and influence how scientists approach the unknown. The atom, once a symbol of mystery and failure, became through Bohr's work a symbol of possibility, pointing toward a deeper and more nuanced understanding of the natural world. The idea of quantization marked one of the most radical breaks from classical thinking in the history of science, and in the context of atomic theory it represented a complete reimagining of how nature operates at its most fundamental level. Before the emergence of quantum ideas, energy was assumed to be continuous, capable of changing smoothly by any amount. This assumption felt natural because it matched everyday experience. A moving object can slow down gradually, a heated object can cool little by little, and light can seem to vary in intensity without limit. Yet experiments at the turn of the 20th century repeatedly contradicted this picture, revealing that at microscopic scales, nature behaved in discrete steps rather than smooth flows. The birth of quantization began as an act of desperation. When classical physics failed to explain the spectrum of radiation emitted by heated objects, Max Planck introduced the notion that energy could only be exchanged in fixed units. This assumption solved the immediate problem, but it also opened a conceptual Pandora's box. If energy was not continuous, then one of the most basic assumptions of classical physics was wrong. Initially, quantization was treated as a mathematical convenience rather than a statement about reality. Many physicists hoped that deeper classical explanations would eventually remove the need for such an unnatural assumption. What Niels Bohr did was to take quantization seriously and place it at the very heart of atomic structure. In his atomic model, quantization was not an add-on but a foundational principle. Electrons were allowed only certain energies, and these energies determined everything from atomic stability to the light atoms could emit or absorb. This move transformed quantization from a technical trick into a central organizing concept. It suggested that discreteness was not a flaw in our theories, but a fundamental feature of nature itself. The implications of this shift were profound. Quantization introduced natural limits where classical physics predicted none. Electrons could not gradually spiral into the nucleus because there were no allowed energy states between certain levels. Stability emerged not from continuous balance, but from discrete permission and prohibition. This idea challenged deeply ingrained intuitions about motion and change. In the quantum view, change could be sudden, discontinuous, and governed by rules that had no classical analog. Quantization also reshaped the meaning of explanation. In classical physics, to explain a phenomenon was to trace a continuous causal chain. In the quantum framework, explanation often meant identifying allowed states and transition rules. The emphasis shifted from describing processes in time to describing structures of possibility. This structural approach proved extraordinarily powerful, even though it left many questions unanswered about what happened between observable events. The acceptance of quantization paved the way for modern quantum theory. It provided the conceptual foundation upon which later developments, such as wave mechanics and matrix mechanics, would be built. Although Bohr's original model would eventually be superseded, its core insight, that nature at the atomic level is quantized, remained central. Quantization became a universal principle, governing not only atomic spectra, but also chemical bonding, solid-state physics, and countless technologies. Beyond its technical impact, quantization altered how scientists thought about knowledge itself. It suggested that nature imposes limits on what can be known and how it can be described. Certain values are allowed, others forbidden, and no amount of refinement can bridge the gap between them. This realization encouraged a more humble view of scientific understanding, one that accepts boundaries as intrinsic rather than temporary. In embracing quantization, physics underwent a transformation from a science of smooth continuities to one of discrete possibilities. This transformation was unsettling, but it proved essential for progress. Quantization revealed a hidden order beneath apparent randomness, an order that could only be understood by abandoning classical expectations. Through this shift, the quantum theory was born, forever changing humanity's understanding of the atom and the fundamental structure of reality. Niels Bohr's principle of complementarity represents one of the most profound and challenging contributions not only to physics but to human thought itself. It emerged from the growing realization that quantum phenomena could not be fully captured by any single classical concept. As experiments accumulated, It became increasingly clear that light and matter behaved in ways that were mutually contradictory when described using familiar ideas. In some experiments, light behaved unmistakably like a wave, producing interference and diffraction patterns. In others, it behaved like a stream of particles, delivering energy in discrete packets. Attempts to force one description to exclude the other led only to confusion and paradox. Rather than choosing between wave and particle descriptions, Bohr proposed something radically different. He argued that both descriptions were necessary, but that they could not be applied simultaneously. Each description was valid only within a specific experimental context. This was the essence of complementarity. Wave and particle pictures were not rivals competing for truth. They were complementary aspects of a deeper reality that could not be fully captured by either alone. This idea required a profound shift in thinking, because it challenged the classical assumption that physical objects possess well-defined properties independent of how they are observed. Complementarity arose from Bohr's deep engagement with the experimental realities of quantum mechanics. He observed that the outcome of an experiment depended crucially on how it was set up. An apparatus designed to measure particle-like properties necessarily destroyed wave-like information, and vice versa. This was not a technical limitation that could be overcome with better instruments. It was a fundamental feature of nature. The conditions required to observe one aspect of a quantum system were incompatible with those required to observe the complementary aspect. This insight had enormous implications for the concept of objectivity. Classical physics assumed that properties such as position, momentum, and trajectory existed independently of observation. Measurement merely revealed what was already there. Complementarity undermined this assumption. In the quantum domain, properties could not be meaningfully defined without reference to the measurement context. What could be said about a system depended on how it was questioned. This did not mean that reality was subjective or arbitrary, but that it was structured in a way that resisted complete description from a single viewpoint. Bohr emphasized that classical concepts were still indispensable. We cannot describe experiments, instruments, or results without using classical language. However, these concepts must be applied with care. They are tools, not mirrors of reality. Complementarity acknowledged both their necessity and their limitations. Classical descriptions remain valid within certain contexts, but no single classical description can exhaust the content of quantum phenomena. The principle also addressed the growing role of probability in quantum theory. In classical physics, probability reflects ignorance about underlying details. In quantum mechanics, probability appears to be fundamental. Complementarity helped clarify this by showing that uncertainty was not merely a lack of knowledge, but a consequence of the mutual exclusivity of experimental arrangements. When one aspect is sharply defined, the complementary aspect becomes inherently indeterminate. This is not because information is missing, but because nature does not allow both aspects to be simultaneously well-defined. Bohr's ideas were met with both admiration and resistance. Some physicists found complementarity enlightening, a way to make sense of the strange dualities revealed by experiments. Others found it unsatisfying, arguing that it replaced clear explanation with philosophical resignation. Critics questioned whether complementarity truly explained anything or merely described limitations. Bohr responded that recognizing limits was itself a form of understanding. To pretend that classical concepts could be stretched indefinitely without breaking was, in his view, a deeper misunderstanding. Complementarity also extended beyond wave-particle duality. It applied to other pairs of physical quantities, such as position and momentum, which cannot both be precisely specified at the same time. These relationships were later formalized mathematically, but Bohr's contribution lay in interpreting their meaning. He saw these limitations not as defects of theory, but as reflections of how nature is organized. Certain aspects of reality exclude each other, yet both are necessary for a complete account. The philosophical reach of complementarity went far beyond physics. Bohr himself suggested that similar principles might apply in other domains of knowledge. For example, in psychology, one might need complementary descriptions of human behavior that cannot be reduced to a single framework. In biology, mechanistic and functional explanations may both be necessary yet mutually irreducible. Bohr did not claim that quantum mechanics directly applied to these fields, but he saw in complementarity a general lesson about the structure of understanding. At its core, complementarity represented a new relationship between knowledge and reality. It rejected the idea that complete knowledge must take the form of a single, unified picture. Instead, it proposed that completeness might consist in the totality of mutually exclusive, but jointly necessary descriptions. This was a radical departure from classical ideals of explanation, which sought to reduce all phenomena to a single coherent framework. Bohr's insistence on complementarity also shaped the culture of physics. It encouraged openness to paradox and patience with ambiguity. Rather than rushing to resolve contradictions, physicists were urged to examine what those contradictions revealed about the limits of their concepts. This attitude proved essential as quantum mechanics developed, because many of its features resisted intuitive interpretation. Complementarity remains one of the most debated aspects of Bohr's legacy. Some later interpretations of quantum mechanics attempt to move beyond it, seeking deeper underlying realities or alternative frameworks. Yet even these efforts are shaped by the questions Bohr raised. Whether one accepts complementarity as a final word or a stepping stone, its influence is undeniable. Ultimately, complementarity reflects Bohr's broader intellectual vision. He believed that understanding nature requires humility, flexibility, and respect for the conditions under which knowledge is obtained. By accepting that certain truths can only be accessed in mutually exclusive ways, Bohr offered a way to live with the strangeness of the quantum world without denying its reality. Complementarity did not remove mystery from physics. It taught scientists how to think responsibly in the presence of mystery, transforming confusion into a deeper, more nuanced form of understanding. Niels Bohr's influence on the development of quantum physics extended far beyond his own theoretical contributions, shaping the scientific community through his role as a mentor, organizer, and intellectual leader. While his atomic model and philosophical insights laid critical foundations, it was his ability to create an environment where revolutionary ideas could flourish that truly defined his impact. Bohr understood that scientific breakthroughs are rarely the product of isolated genius alone. They emerge from dialogue, disagreement, and sustained collaboration. With this understanding, he devoted immense energy to building institutions and fostering relationships that would nurture the next generation of physicists. The establishment of the Institute for Theoretical Physics in Copenhagen, later known as the Niels Bohr Institute, became one of the most important events in the history of modern science. It was not designed as a hierarchical institution where knowledge flowed in one direction from master to student. Instead, it functioned as an open forum, a place where ideas could be freely exchanged, challenged, and refined. Young physicists from across Europe and beyond were drawn to Copenhagen, not only by Bohr's reputation, but by the unique intellectual atmosphere he cultivated. Bohr's mentoring style was distinctive. He did not lecture in a rigid or authoritarian manner. Conversations with him were often slow, meandering, and demanding. He asked questions that forced his colleagues to clarify their assumptions and confront the limits of their understanding. This process could be frustrating, but it was also deeply productive. Bohr believed that true understanding emerged through struggle, not through the passive absorption of answers. He encouraged his students to think independently, even when their ideas conflicted with his own. Among those influenced by Bohr were some of the most brilliant minds of the 20th century. Physicists such as Werner Heisenberg, Wolfgang Pauli, and others developed key components of quantum mechanics while in close contact with him. Although their mathematical approaches sometimes diverged sharply from Bohr's own thinking, The conceptual framework within which they worked was profoundly shaped by his ideas. Bohr provided a philosophical anchor, helping to interpret the abstract formalism of quantum mechanics and relate it to physical reality. The collaborative culture at Copenhagen was marked by intense discussion and intellectual honesty. Ideas were not accepted because of authority, but because they survived critical examination. Bohr welcomed disagreement, viewing it as essential to progress. He was known for his willingness to revise his own views in light of persuasive arguments or new evidence. This openness created a sense of shared ownership of discoveries, blurring the line between individual and collective achievement. Bohr's leadership also extended beyond the walls of his institute. He played a central role in international scientific communication at a time when Europe was deeply divided by political and social upheaval. Conferences and informal meetings provided opportunities for physicists from different countries to exchange ideas and build professional relationships. Bohr saw science as a fundamentally international endeavor, transcending national boundaries and political conflicts. This belief in internationalism was not merely idealistic. It was grounded in Bohr's understanding of the nature of scientific knowledge. He believed that no single perspective could capture the full truth of complex phenomena. Just as complementarity required multiple, mutually exclusive descriptions, scientific progress required diverse viewpoints and collaborative effort. This philosophy shaped his approach to institution, building and mentorship alike. Bohr's influence as a mentor was not limited to technical matters. He also shaped the ethical and philosophical outlook of those around him. He encouraged physicists to reflect on the broader implications of their work, including its social and moral dimensions. This concern became especially important as quantum physics laid the groundwork for technologies with enormous destructive potential. Bohr later emerged as a vocal advocate for international cooperation and responsible use of scientific knowledge. But the roots of this stance lay in his early leadership within the scientific community. The legacy of Bohr's mentorship can be seen in the way quantum mechanics developed as a collective enterprise. No single individual can claim sole credit for its creation. Instead, it emerged from a network of thinkers who influenced and challenged one another. Bohr's role in this network was unique. He was not always the most mathematically innovative, but he was often the conceptual center around which discussions revolved. His ability to synthesize ideas and articulate their broader meaning helped give coherence to a rapidly evolving field. Bohr's institute also set a model for how scientific institutions could function. It demonstrated that fostering creativity requires more than funding and facilities. It requires an atmosphere of trust, openness, and intellectual courage. By prioritizing dialogue over hierarchy and curiosity over certainty, Bohr created a space where radical ideas could be explored without fear. In assessing Bohr's contribution as a mentor and leader, it becomes clear that his impact cannot be measured solely by publications or discoveries. His true legacy lies in the people he influenced and the culture he helped create. Through his guidance, countless physicists learned not only how to do science, but how to think about science. They learned to respect experimental evidence, to question assumptions, and to accept the limits of understanding without surrendering the pursuit of knowledge. Bohr's leadership during the formative years of quantum mechanics ensured that the field developed with both intellectual rigor and philosophical depth. By bringing together diverse minds and encouraging open exploration, he helped transform a collection of puzzling experiments and tentative ideas into one of the most powerful and successful theories in the history of science. His role as a mentor and institution builder stands as a reminder that scientific revolutions are as much social achievements as intellectual ones, shaped by communities as well as by individuals. The legacy of Niels Bohr extends far beyond the historical moment in which he worked, reaching deeply into the foundations of modern science, technology, and human understanding. His ideas did not remain confined to academic debates or theoretical papers. They reshaped the way humanity interacts with the physical world. By transforming the atom from a mysterious abstraction into a system governed by intelligible, though counterintuitive, principles, Bohr helped unlock a cascade of discoveries that continue to define contemporary life. One of the most immediate and tangible impacts of Bohr's work can be seen in the technological revolution driven by quantum physics. The concept of discrete energy levels lies at the heart of technologies such as semiconductors, lasers, and magnetic resonance imaging. The electronic devices that power modern communication, computing, and medicine rely on principles that trace directly back to Bohr's insights into atomic structure. Without the understanding that electrons occupy quantized states and transition between them in predictable ways, much of modern electronics would be impossible. Beyond technology, Bohr's influence reshaped the direction of scientific research itself. His insistence that experimental results must guide theory, even when they conflict with intuition, became a defining principle of modern physics. This approach encouraged scientists to explore realms that defy everyday experience, from subatomic particles to cosmological phenomena. Bohr helped establish a culture in which strangeness was not a sign of error, but a potential sign of deeper truth. Bohr's philosophical contributions also left a lasting mark. His views on complementarity and the limits of knowledge challenged the classical ideal of a single, complete description of reality. Instead, he proposed a more nuanced understanding in which different perspectives are necessary to capture the full richness of phenomena. This idea resonated beyond physics, influencing discussions in philosophy, epistemology, and even the social sciences. It encouraged thinkers to accept complexity and ambiguity as inherent features of understanding, rather than obstacles to be eliminated. The impact of Bohr's thinking can also be seen in how science grapples with uncertainty. Classical physics sought absolute predictability, but quantum mechanics introduced fundamental limits to what can be known. Bohr did not view these limits as failures, but as insights into the structure of reality. This shift in attitude transformed uncertainty from a problem to be solved into a feature to be understood. It laid the groundwork for probabilistic reasoning across scientific disciplines. Bohr's legacy is also inseparable from his ethical stance. Having witnessed the application of atomic physics in warfare, he became a strong advocate for international cooperation and the responsible use of scientific knowledge. He believed that the power unlocked by understanding the atom imposed a moral obligation on scientists and governments alike. His calls for openness and dialogue during the nuclear age reflected the same principles that guided his scientific work: respect for complexity, recognition of limits, and commitment to shared understanding. In education, Bohr's influence persists in how physics is taught and learned. His atomic model, though simplified, remains a foundational step in introducing students to quantum ideas. More importantly, his approach to learning, emphasizing questioning, discussion, and conceptual clarity, continues to inspire pedagogical practices. Bohr showed that deep understanding arises not from memorization, but from engagement with fundamental questions. The cultural impact of Bohr's work is subtler but equally profound. By revealing a universe governed by probabilities and complementarities, quantum theory challenged deterministic worldviews that had dominated Western thought for centuries. Bohr's interpretations helped society come to terms with a reality that is less predictable and more relational than previously imagined. This shift influenced how people think about causality, choice, and the nature of truth. Bohr's legacy also lies in the scientific community he helped build. The collaborative, international culture of modern physics owes much to his example. By fostering dialogue across borders and disciplines, he demonstrated that scientific progress thrives on openness rather than isolation. This model remains crucial in addressing the complex global challenges of the present, from climate science to emerging technologies. Perhaps the most enduring aspect of Bohr's legacy is the way he redefined what it means to understand nature. he taught that understanding does not always mean reducing phenomena to simple pictures or definitive answers. Sometimes, it means recognizing the conditions under which knowledge is possible and accepting that different descriptions may be required for different questions. This lesson extends beyond physics, offering a framework for thinking about complexity in all areas of human inquiry. In reflecting on Bohr's impact, it becomes clear that his genius was not limited to a single discovery or theory. It lay in his ability to reshape the intellectual landscape, guiding humanity toward a deeper and more humble engagement with reality. By unlocking the quantum atom, Bohr opened a door to a world that is both more mysterious and more interconnected than classical physics ever imagined. His work reminds us that progress often requires letting go of certainty and embracing the challenge of understanding a universe that continually exceeds our expectations.